Okay, everybody, welcome back to another instance of the undergraduate seminar. Today, Jesse Maltese is going to give us an introduction to mathematical logic. I'm super duper stoked for this talk, and I'm glad that you're all here today. Thank you very much for coming out. Jesse, take it away.
Hi, everyone. Thanks to Professor Elisa and Professor Parker for hosting this series. I'm really glad to be here. Just quickly, I'm a third year. I'm going into my third year at the University of Toronto, Scarborough, with a specialist in math and a major in computer science, and a minor in computer science and another minor in philosophy. Today, we're going to be talking about mathematical logic, as it says on the screen. So we'll just look at an outline really quick and sort of discuss what you kind of need to understand the stuff in this talk, and then what we'll talk about today. And so I've sort of set the prereqs as first order logic. So this is sort of knowing what the symbols mean, really. And so if you're at UTSC, A67, B36, PHL B50, these kinds of courses will give you the appropriate knowledge to be able to talk or be able to understand what I'm talking about today. Sorry, there's a bit of noise. The first thing we'll talk about is sort of what is mathematical logic. Well, we're going to try to answer this question. And we'll talk a tiny bit about the history of the field and sort of how the field has developed through the years, and where the field is now, and a little bit more about the applications of the field. And then we'll look at sort of the core ideas, which are what I deem the core ideas, so languages, structures, and truth. And then we'll look at two of the fundamental theorems of the field, so completeness and the compactness theorems. And if we have time, we'll try to discuss some of these two really interesting problems that I want to talk about. Hopefully we'll have time for at least the 4-color theorem, because it's really cool and quite simple. So let's dive right into it and try to answer the question of, what is logic? Because that's an important question to answer, because I think people have a notion of what logic is, right? They have some idea of maybe it's in the philosophical sense of like of reasoning or philosophical logic, or maybe they have the philosophy of logic idea of it, or maybe just the natural sort of language sense of logic of like, logic is correct reasoning. And these are all sort of connected, but they're not what we're talking about when we say mathematical logic. Mathematical logic as a field is sort of concerned with really, really broadly, two ideas. And so the first one is sort of, if we consider some sort of system of proof, we kind of want to be able to talk about how much power do we have in that system of proof? What can we say? What can we not say? What can we prove given some set of axioms, and how strong is that set of axioms? Stuff like that. And that's not our big concern today, but that is sort of that's what the field of proof theory, and to some extent the field of computability theory, talk about. But the other field, and that's sort of our main interest today, is sort of the expressive power of formal systems. And what does this mean? So in our context, the formal system is something like first order logic, but a formal system in general is sort of any sort of thing that has some language, some formal language. So, but we're talking about specifically first order logic. I'll just write FOL. And so the kind of, sorry, someone's mic is, or someone's typing quite loudly. I don't know.
Oh, I'm so sorry. That's one of your diligent organizers, and I'm being disruptive. My apologies.
Sorry about that. Cheers. So what we kind of talk about is expressive power. And so what does this mean? So we kind of want to be able to talk about, given some system, we want to be able to ask, what does it mean to be true? What does it mean when we have some sentence, and what does it mean to be true in that sentence, for that sentence to be true? We also want to ask, if something is true, can we actually prove that it's true? Which is something that we'd really like to have, right? It'd be great if we could prove the stuff that was true. And if something is provable, is it actually true? And this is like super important, because we want to be able to write proofs that actually mean something. If we're trying to prove something is true and we prove it and it turns out to be false, well, that was a waste of our time. That's really sad. And this final point of kind of what expressive power means is sort of technical. And if we consider some set of axioms like Euclidean geometry, so Euclidean geometry, like in an informal sense, it's about 4 or 5 axioms, right? And they all sort of make a claim, but we can interpret these axioms in different ways. And this is sort of in a really informal way of interpreting them, and we'll formalize this later. But if we interpret these axioms in different ways, we can sort of say different things using the same axioms. And so mathematical logic, and specifically this field down here called model theory, sort of asks the question, if we interpret things in different ways, what can we say about every interpretation of some set of axioms? Or what can we say about certain interpretations of set of axioms? Or what can we just say about every interpretation in general? And then there's also this little idea on the side that's super important, sort of what can we define in this interpretation? And these are all connected, and we'll get to some of them today, and we won't get to some of them today. But I just wanted to, kind of hopefully give, well, not a satisfying answer in any sense, something that kind of gives you an idea of what we talk about when we're talking about mathematical logic. And so the first thing I want to do is quickly go through some history of our field, and I'm starting at a place of Hilbert, David Hilbert. And so what David Hilbert's sort of function in the mathematical logic field is you kind of need some history and some background. So if you go back to around the 1800s, we had all these sort of informal and nebulous ideas of what math was. So for instance, like in calculus, we had this idea of a limit, and a limit wasn't formalized. A limit was just like something kind of gets really close. There is quite a bit of rigor of what an interpretation is, and we're gonna talk about that. It's a great question, Ben. So we'll talk about it in a few slides. But yeah, there is definitely a very formal sense of interpretation. But for now, your informal idea of what interpretation is will do. But anyways, in the sort of the start of the field, we had this idea that like in calculus, an infinitesimal or a limit is like something getting really close. And that was the idea that Newton and Leibniz were kind of working off of. And then around, I don't know the exact date, maybe the 1750s or so, people started saying, this doesn't work. We're doing a lot of like really abstract stuff now. And this idea of like saying a limit is just something that gets really close isn't satisfactory. And in fact, like people like Weierstrass, who found this function that was continuous everywhere but differentiable nowhere, or stuff like that, and like people like Galois and Nabel, who are formalizing group theory, they were all doing really absurd, like abstract math, and this informal notion that we had of what math wasn't cutting it. And so there are people sort of through the 1800s that were working to formalize in certain fields. So for instance, Bolzano came up with the epsilon delta definition of a limit. And that's like a formal thing that you learn. And it's like a formalization of the concept of a limit. And we were slowly formalizing all of these different ideas in different fields. But what we didn't have was some formalization of a foundation of the entire field. And that took up quite a bit of the 1800s, where people were just thinking like, is this a possible formalization? Is this a possible formalization? And what we came up with was that we need a set theory. We need a way to, like, if we have some like hierarchy of math, or maybe like, I don't know, calculus is at the top, which is sort of a weird place to put the top. But nonetheless, we have a bunch of other fields. We need something down here that we can talk about and say, this is like the foundations of our field. And nowadays, a mathematician would say, this is ZFC. This is a set theory that we use, and most working mathematicians work with, ZFC. But in the 1800s, they didn't really have a sense of what this foundations was. And so a guy named Gottlob Frege, who's a philosopher, mathematician, philosopher of math, sort of kicked off this idea of formalization of set theory, and something that we now call naive set theory, or NST. And so this formalization of set theory it kind of did everything we wanted it to do, because we could formalize the stuff on top of it, and it made sense intuitively, and it was formal, it was rigorous. But in 1901-ish, a guy named Bertrand Russell, I'll write B. Russell, he proved something that you never want to have happen in your foundations. And he proved that there was a contradiction within NST. Oh, do we need this for anything? So I'll explain that right now, actually. So what Bertrand Russell proved was that you could essentially, in naive set theory, you could prove this statement. X and S if and only if X is not in S. And this is where S is just some set. And immediately you should see this is not okay to be able to prove, because this is a direct contradiction, and you could prove this from within NST. And so if you can prove a contradiction within your system, there's something called the principle of explosion. And it's something that you learn in symbolic logic. And a principle of explosion just says, if you can prove a contradiction, then you can prove literally anything. And so if you can prove a contradiction, if you can prove literally anything, there's no point in proving anything. And so if you sort of have, my answer to Ben would be, is if you sort of correlate rigor with proof, and then if you want your proof to be valuable, you don't want an informal system, because if you have an informal system, you're going to end up with an inconsistent one, most clearly, right? And so once we found this out in the 1900s, people sort of were scrambling, and they were saying, oh no, this is terrible. This is not what we want to have happen. And there were a bunch of schools of philosophy of math and of formalization schools that popped up in the 1900s. And the main one that popped up was the one led by David Hilbert, this guy with the really nice hat on the screen. And David Hilbert's school was called the formalist school of the philosophy of mathematics. And I say philosophy of mathematics, but it was really concerned with, the foundations as a whole. And so Hilbert's school sort of set out to do a few things. He essentially wanted to write down a list of rules for mathematics that satisfied three things. He wanted them to be consistent in the sense that there's no contradictions. We can't have a contradiction. He wanted his rules to be complete in the sense that if something was true, then we could prove it. And that's something you would really love to have. If we can prove, if it's true, then there's a proof. And finally, I'm going to move this down actually. And finally, he wanted it to be decidable. And I don't think they would have called it decidable in the 30s because this notion wasn't around, but he wanted it to be that essentially any sentence you can write down, there's either a proof of it or its negation. So either we can prove that phi is true or not phi is true. We always want to be able to prove one of these. And David Hilbert's program in this school took up about, well, pretty much the entirety of the 1920s. And I think some of you might know where this is going, but around 1929, 1930, a guy named Kurt Gödel burst onto the scene. And Kurt Gödel came out with his PhD thesis, and then another theorem, and then the incompleteness theorem, this triple sweep that sort of revolutionized the field of logic. And the main theorem in the context of Hilbert was this theorem. And this incompleteness theorem, there's two of them, so we say theorems, but 1 and 2. And what the incompleteness theorems did was essentially, and we won't get into this too much just yet, he essentially said, sorry, Hilbert, we can never have this. We can't have consistency. And then he said, also, Hilbert, we can't have decidability. But then he also said, but we can have completeness, and we can have some sense of completeness. And everyone was really happy about this, or everyone was really sad about the first two, but the second one, or the third one, the completeness, is quite a nice thing to have. And so that was sort of Gödel's contribution to the field. And we're going to talk about these first two theorems here in some depth today. Which one was completeness? What do you mean up here, or this theorem? We'll talk about the completeness theorem. Sorry?
What is completeness?
So completeness up here means this sense of completeness is if it's true, then we can prove it. Okay. Logicians are weird, or logicians just choose really bad terminology in the sense that it's called the incompleteness theorem, but really it says something about decidability in this notion, this word decidability. So either we can prove something or we can disprove something. And so this was sort of Gödel's contribution to the field. And all this stuff in the 30s kind of revolutionized logic as a whole and brought it onto like the forefront of the field of math. And the field obviously didn't die in the 30s, and there are still lots of people, and there were lots of people working on other things in logic. And so logic today, if you're familiar with like current logic or current model theory or research in general, it kind of is concerned with connections to other fields. So we talk about stuff like, model theory and topology, model theory and geometry, model theory and etc. I'll read that later. We talk about connections to other fields of math, but we also talk about, internally, like we answer interesting questions inside of our own field, right? I had the idea to look at one interesting theorem that is a connection between model theory and algebra called Glynn-Adey. I don't know if we'll have time. I doubt it. But anyways, model theory or logic in general also has connections to other fields. So I know there's a lot of computer scientists in the chat, and of course, computability is a super important field for the theory of computation. There's lots of logical ideas in programming language theory. Essentially, a functional language. I know we have Professor Albert Lai in the chat, and functional languages like Haskell are sort of founded in a lot of mathematical logic ideas and type theoretic ideas, right? So stuff like this is sort of founded in logic, and there's stuff like the Howard-Curry correspondence, or Curry-Howard, I don't know what it is, which sort of talks about, programs are proofs. Stuff like this is all founded in the idea of logic, and all points to applications of logic into other fields, and into computer science especially. So stuff like safety critical software and provable software, stuff like this is all based in logic. And I'm just throwing out terms right now, because if you're interested in this, these are great things to Google, and they're great rabbit holes to fall down. But anyways, that sort of concludes my rambling about the history. Let's get into some serious math now. And the first thing we need to talk about when we're talking about first order logic is what a language is. And so we kind of have an idea of what we need in a language at the bare minimum. And what we need in a language at a bare minimum are all of our standard logical connectives. So these are the things like negation, conjunction, disjunction, implication, if and only if, and then also the left and the right parentheses. As well, we need at least one quantifier. Usually people write two because it makes life easier. We need at least two. We need a universal and these existential quantifiers. And then finally, we need a countable collection of variables or things to quantify over. So I write V1, V2, and there's infinitely many of these, etc. And then the next thing we need is sort of this idea of a signature of a language, or the thing that characterizes a language. And so what does it mean to characterize a language or give the signature? It means give the things that define it, because everything up here is in every language. That's important. Every first order language, or every language, always has these things. But what every first order language doesn't always have are the same predicates, the same functions, and the same constant symbols. And so predicates are essentially things like the less than symbol, or the greater than symbol, or the symbol that says like x is divisible by y, or x divides y, stuff like this, or maybe some predicate that says x is prime. Any sort of thing that takes in terms and returns a truth value. That's what a predicate is. And we in any language you specify, we have a certain amount of these, and they're unary, binary, trinary, n-ary, essentially. And then we have function symbols. And so the next thing these function symbols are stuff like addition, multiplication, subtraction, etc. And these are sort of things that take in two values, two terms, and return another term in our language or in our domain. And finally, we have this thing, these constant symbols. And constant symbols are just the idea of like fixing something in our language. So for instance, fixing 0 in the theory of arithmetic. We want to fix 0 because sort of 0 is our first thing, and we base everything off of 0. And then I have this mentioned down here of whether or not we include the identity symbol. And I don't want to get into this too much, but essentially identity is special. And so we can't just call it a predicate. We need to sort of include it separately. And we could have an empty language. This is what I say down here. We could have an empty language. So there's not necessarily a predicate, a function, or a constant symbol in any language. And so this is a language. Let's look at a nice example of one, which is the language of arithmetic. And so the language of arithmetic is a simple language in which we have one constant symbol, O, one function symbol, S, two binary function symbols, plus and times, and then one binary relation symbol, less than or equal to. And sort of, it's hard to explain this, but essentially these are just symbols. So we have some connotation of what these all mean. Like we kind of know what it means to say 2 + 2 or whatever, but in this language, there's no such thing as a sentence 2 + 2. And there's especially no such thing as this as of the semantics that we might associate with saying 2 + 2. So everything is sort of uninterpreted, if that makes sense. And it probably doesn't make sense, and we'll talk about it a bit more later. But anyways, within a language, because stuff is uninterpreted, we need to be able to assign meaning to it. And so Ben asked earlier, what do I mean by interpretation? And so we're going to talk about that. And so what an interpretation is essentially a thing that takes symbols from our language and it assigns some meaning to them. And so the first thing I define up here is something called the universe. And I just say universe because it sounds cool, but some people say domain of discourse. They're both like the same thing. And what the universe is sort of the things that we're talking about in our language. And so we have this idea of an interpretation function. And an interpretation function takes things in our language and it outputs them into things in the universe. And so for any sort of predicate, we interpret the predicate and it gives us back a subset of the Cartesian product of our universe of however many, n times that the n-arrayness of the predicate, right? So we'll look at an example later if this doesn't really make sense. Similarly, for any sort of n-place function symbol, it gives us back a function, an n-array function on the universe. And then finally, for any sort of constant symbol, it gives us back just some singular element in our universe. And this is sort of what an interpretation function is. And this is sort of, this is quite opaque, I think. So some examples will be helpful. And so the first thing we need to quickly define is that a structure is something, because we can never talk about a universe or an interpretation without a universe and a universe without an interpretation, we always sort of bundle them together into one thing, and it's called a structure. And structure is really just a notational convenience to bundle an interpretation and a universe together. So let's look at our first simple example, and that is we consider some language with a single element or a single relation, which is less than or equal to. And then what we do is we interpret this. So we have our universe being the rational numbers and our interpretation function I, which sends, and this is a big error, my fault, my bad. This should say less than or equal to, and this shouldn't be there. I think I copied the wrong, I copied the wrong slide set, my bad. But anyways, what we do is we interpret I, and we say I is the standard order on Q. So I says like, 1/2 is less than 1, for instance, and that's all I is. And this is just a really dead simple idea of an interpretation and of a structure. Let's see if I copied the wrong slide set. I didn't. Great. Okay. So our next sort of example is the idea that we can sort of modify what it means to say to interpret something. So I take the same structure over the same language in the same universe, so the rationals. But what we do is instead we interpret our less than or equal to symbol to be, taking the mod 3 of each side of our statement. So the example I give is that we can write then that 4 is less than or equal to 2, because we're actually considering 4 mod 3 and is less than or equal to 2 mod 3, which is of course saying 1 is less than 2, right? So this is just the idea of sort of interpreting symbols in our language differently. And the final simple example I give is this sort of a goofy one, and I typed it out wrong, but this should say 3/2, but it's a lexicographic ordering. And so what I mean by this is that we consider elements of Q to be their fractional components in a tuple, and we say like 3/2 is less than or equal to 1/2 because 3 is less than 1. And this is a lexicographic ordering, it's called. And this is just another example of how we can sort of reinterpret the same symbol a bunch of different ways and get completely different results when we do that. And a really important interpretation or structure is a structure for arithmetic. And so this is like the one that everyone learns first. And that's because it's the most important in some sense. And so what our structure for arithmetic is it starts with a universe. 1 is less than or equal to 3. Sorry, oh, Lord, my bad. I messed up my example, but you're right, Lyndon. Yeah, I completely messed up this example. Flip these around or something, sorry, and it'll make sense. I'm sorry about that. But anyways, it's lexicographic ordering. This is the actual meaning of the sentence. I'm sorry, I don't know how I messed it up. That's so embarrassing. Anyways, the standard model for arithmetic is we consider some universe that are in our normal standard universe is the natural numbers. And then we interpret this O symbol that we talked about earlier to be as a constant, and it's interpreted to be 0. We interpret less than, we interpret less than to be less than. We interpret successor to be adding 1. We interpret plus to be plus, and we interpret times to be times. And this is really weird, I think, to look at, because we're saying, we're defining plus to be plus. How can we do that? And the reason we can do that is that plus on this side is sort of talking about some sense of plus is just a symbol. It's just like a glyph on my screen, or as we would say in the object language, right? Whereas plus on this side is referring on the right side is referring to this sort of interpretation of plus as in colloquial English, maybe, so to speak, or just general math. And so we can say plus equals plus because plus on the left side is the symbol in the language, whereas plus on the right side is sort of humans speaking about what addition means. And this is sort of a goofy concept, but it's an important one in logic. And so, yeah, that's what the language of arithmetic is. But an interesting idea in the language of arithmetic is that if I were to write down something like S of O plus S of O equals S of O, which sort of translates to being 1 plus 1 equals 2 in the standard interpretation, we don't really have a way of assigning a truth value to this sentence if it didn't have a standard interpretation. We don't know what this means to be true, right? Because we kind of know what equality means in general, but we don't know what S of O is, and we don't know what S of O is, right? And we don't even know what O is, because I could redefine S to be like a different value essentially, and it would change what this means. And so this sort of brings up the idea of what is truth, or how do we talk about truth? Because in zero order logic, or I call it zero order, but I think it's called propositional logic normally, something like the truth value of a statement like this: P implies Q if and only if not P or Q. This is a standard statement that you would see in like your first symbolic logic course. And I think it's a tautology. But if I were to ask you the truth value of this, you would be able to look at it and be like, oh, I know the truth value of this. This is true because I can do something really cool. I can simply just write down a truth table. I can do this with I can write an algorithm to write down a truth table for this. And it tells me that this is true in any variable assignment or truth assignment of P and Q. And so we don't really need to worry about what P means and what Q means, because we know what implication is. And P and Q are just like some random symbols. But if we were to consider this sentence that I've written down here, for all x, for all y, P of x implies that there exists a z such that P of xz and P of zy. And I were to ask you to tell me the truth value of this, I won't ask anyone to try, but I would hope that if you did try to tell me the truth value of it, you would say, I don't know, there isn't one. This literally doesn't have a truth value. Because we don't know what it means to say for all x, because we don't know what sort of universe we're pulling from. And we don't know what it means to say pxy. Is pxy that x and y are prime? Is it that x is divisible by y? I don't know. And so there are some interpretations where this sentence is true. For instance, if we consider that our universe is the real numbers, and we consider that P of xy means that x is like strictly less or less than y, then we can interpret this as density of the real numbers, and then it would obviously be true, right? But there are other interpretations, and I can't think of one off the top of my head, where this would immediately fail. And so this sort of gets at the idea that truth is relative to an assignment, or truth is relative to an interpretation. And so to talk about truth, we can't just look at the syntax. We need to consider the semantics of our sentence. And so the upshot of this sort of is that we need to translate, and this is in a really loose sense, we need to translate a sentence out of its syntactual form and into its sort of meaning, its actual meaning. And so let's look at like a sort of an example of a translation, which is that I consider this simple sentence. There exists an x such that for every y, x is less than or equal to y. And if we consider this over the standard model, we would say that phi is true relative to this model. Yeah, that would work. Yeah, obviously that would work. Great. That's a good example of something where it would fail. Right. So if we consider phi true relative to the standard model of arithmetic, we would say phi is true relative to m if and only if, and then we sort of translate phi into natural language using our interpretation that we know of the symbols. So we say there exists an x in the universe n, such that for every y in the universe n, x is less than or equal to y. And this is true. There exists an x in the universe. There's 0 specifically that is less than or equal to every other element in the natural numbers. And so this is true because we've interpreted it relatively, right? We've taken what each symbol means in our structure, and we've interpreted it, and we can look at it and say, oh, this is totally true. And so this gets at the idea of what a translation is. And how we talk about truth. And so the way we talk about truth, this is really informal, but it's slightly formal, but it's mostly informal, is that we translate the sentence and then determine its truth value from there. And this is where this symbol m satisfies phi comes in. And so what this means is that phi is true relative to our structure or relative to our model. So this is the case if and only if the translation, again, in some sort of nebulous sense, of our sentence is true. And people who know a bit of model theory might call me out and say, this doesn't work if we have free variables. And of course, you're right. And so we're only talking about sentences without free variables right now, because free variables throw a lot of complexity into the system. So this is sort of what it means for something to be true in a structure. And that's great. So now we have a theory of truth. And now we can start talking about sort of properties of structures and properties of languages. So let's get into that now. Quickly, we should mention two notions. So there's this idea of a set of sentences implying some other sentence. And so this is the idea of some set of axioms proving or satisfying some other sentence. So for instance, in the standard interpretation of arithmetic called piano arithmetic, we can prove that a times b plus c equals ab plus ac. And this is we say this is a theorem of piano arithmetic. But this is sort of the idea of logical consequence, because piano arithmetic is a list of sentences, and this is another sentence. We call this phi. And so we have this list of sentences, and it satisfies another sentence if and only if, for any structure, any general structure, such that that structure satisfies every sentence in our set of sentences, like piano arithmetic, then that structure also satisfies phi, our sentence. And so in this case, this would be the case that m satisfies every sentence in piano arithmetic, and then that implies that m satisfies phi. And so this is called logical consequence or semantic implication. And there's sort of a dual to this, and it's called syntactic implication. And you don't need to read this whole thing, but suffice it to say, syntactic implication is the idea that there exists a proof of a sentence from some set of sentences. And the important part about this is that the proof is finite, and the proof uses a few very simple rules to get to this point. And so if you're in PHLB 50, this is a derivation. Or if you've taken, I believe B36 also does this a bit. So this is a derivation. This is the idea that something is provable. And we write the symbol gamma, and then this is called, the LaTeX command for this is v dash, but I say proofs phi. And that's what this means. There is a proof from gamma using only sentences of gamma and a few other axioms that gets to phi. And so now that we have a notion of what this means and what this means, we can talk about general notions in sort of logic. And the first one we kind of want to talk about is for something to have a model. And this is the titular thing in model theory of something being a model. And so for some set of sentences and some structure M, we say that if every sentence in gamma is satisfied by using this satisfied, then we say that M is a model for gamma. And so that means that the interpretation, my screen is frozen, I'm sorry. Oh no, my screen froze. One sec, let me restart. Oh no. I'm so sorry about that. There we go. Okay, so let's start again. So gamma has a model if we can have some structure that satisfies every sentence or makes every sentence true in that translation. And that's all it means to have a model. And we'll talk about, we're going to use this kind of idea a lot. And so this is what it means to have a model. And so the next idea we'll talk about, and we mentioned this at the top of the talk, and we're just formalizing it now, was what it means for a theory to be consistent. So if you'll remember, Russell showed that naive set theory was inconsistent because we had this, X and S, if and only if X and not S. And so what Russell really showed was that NST as a set, because NST was a set of sentences, naive set theory, it was a set of sentences. He showed that it proved X and S, and it proved NST proved that X wasn't an S. And these are exact negations of each other. And so he showed that it was inconsistent. So the idea of consistency is the idea that there is no way that you can prove this. There's no way that you'll ever end up with the case that some single model both proves phi and proves not phi. So that's what it means for a theory to be consistent in a formal sense. And so this brings up a really important idea. If our theory is consistent, if we can prove something, then do we know it's true? And that's obvious. That should be a question that is immediately on your mind when you see some new formal system. We say, if we can prove something in that system, then it's true. And this is called the soundness theorem. And that's exactly what this says. Phi proves, if we can prove phi, then we must have that we can show that phi is true. And I'm giving two equivalent formulations of the soundness theorem here because they're both important. So the first one is just this up here. If we can prove it, then it's true. And the other one is that if gamma has a model, then it's consistent. And recall that gamma has a model if every sentence that we write down is true, or every sentence in that structure or in that set of sentences is satisfied by some model. And so these are sort of two equivalent formulations of this thing called the soundness theorem. So the question that model or logicians like to ask then is, okay, so if we can prove this direction, if we can prove that if it's provable, then it's satisfiable, can we prove this direction? And the answer is yes, we can prove it in first order logic. We can prove that if something is true, then it has a proof. And this is called Gödel's completeness theorem. And so I've written it in a weird way, if a theory is consistent, then it has a model. But this is sort of equivalent to saying that this implies this implies this. These are the same thing. And so then we actually can write down, we can say this is a biconditional because of the soundness theorem. And I'm not going to be giving a proof of this, but what I will mention is a bit of the history, because I think it's quite impressive, is that this is sort of a question posed by Hilbert in the mid-20s. And Gödel, as part of his PhD thesis at Vienna, actually proved this result in 1929. This is PhD thesis, which was amazing, because this is like a really foundational result in theory of first order logic. And this was his PhD thesis, which I just think is really mind-blowing. But anyways, so this is the completeness theorem. And obviously, everyone wants to ask about the incompleteness theorem probably, and I don't think I'm going to have time to talk about it just yet. But if you have a question at the end, I can sort of mention why they aren't negations of each other, because I think that's the natural question to ask. And I'm not going to present a proof of the completeness theorem because it's someone's typing, sorry. Because it's quite complex, and the nicest proof of it I know is uses ultra products, which is something I don't have time to introduce. But anyways, this is the completeness theorem, and we're going to use the completeness theorem to prove another result of Gödel's, which is called the compactness theorem. Sorry, someone's typing again. I think it might be.
Okay, this time it's not one of your organizers.
Oh, okay.
I can just mute everyone other than you.
Sure, that's fine, I guess. So this is the compactness theorem. And the compactness theorem is really, really important, but it's sort of hard to show how important it is without having you done some problems with it. So I'm going to present the proof of it, and then hopefully if I have time, I'll be able to look at an application of it. But the compactness theorem is really a tremendously important result. It was also proven by Gödel. And what it says is that some set of sentences has a model, and recall, having a model means that every sentence is satisfied by some structure, if and only if every finite subset of this set of sentences has a model. And so this is a biconditional. And so this first direction is sort of obvious, right? Because if we have that there is some model such that for every gamma in gamma, that model proves or satisfies gamma, then clearly any finite subset, any restricted subset of all of these is also going to satisfy this. So this forward direction is quite simple. So we'll look at the other direction. This, if every finite subset has a model, does the whole set have a model? And this is the first proof we'll consider today, and maybe the only one. And so here's a proof of compactness, and it's quite overwhelming, but I'll go through it slowly. So the first thing we do is we suppose that this isn't the case. We suppose that every finite subset has a model, but the whole set doesn't. So we've assumed that this part is true, and we've assumed that this part is not true, right? Contradiction. And so what we do is we take the contrapositive of the completeness theorem. And so since we know that gamma doesn't have a model, by the contrapositive, we know that gamma is inconsistent. And so what this means is that since gamma is inconsistent, there is going to be some sentence such that we can prove both that sentence and its negation. And if you recall the definition of what it means to prove something, we know that what it means to prove something is that there exists some finite set of sentences such that it follows from these finite sets in quite a simple way. And so what we can say is that there must exist two finite subsets of gamma such that one of them proves phi and one of them proves not phi. And these don't necessarily need to be the same or different sets. They don't necessarily be proper subsets of gamma, but they're just some subset of gamma that proves phi and some other one that proves not phi. And I call them phi, gamma prime and gamma prime prime. And so clearly then, their union also must prove gamma or phi, and their union also must prove not phi. And this is obvious because, we can, to write the proof down, we just don't include the sentences that aren't used in the proof. And so of course their union must prove it if each of them proves stuff individually. And then also note that for any two finite sets, are we assuming consistency of some set theory for this proof? We aren't assuming, we can never assume consistency of a set theory. That's impossible because of Gödel's incompleteness theorem too. So, but we're just functioning on the idea that our set theory works, I guess. Yeah, right. But we can't assume the consistency of set theory. But yeah, it is kind of weird that I'm using all these. What I'm really asking is, what does finite mean? I'm not clear on what your question means. Sorry, I'll finish the proof and then we'll talk about, well, I'll answer you. So maybe just if you can clarify, I can try to answer. Sorry. But anyways, so we note that the union of two finite sets is finite in some classical sense of finite being, there's an end or whatever. And so we can say that the union of two finite sets is necessarily finite. And this union, gamma prime union gamma prime prime, proves a contradiction because it proves phi and it proves not phi. And so what we have is that, again, by the contrapositive of the soundness theorem, which we have that since gamma is inconsistent, it doesn't have a model. That's by the contrapositive of the soundness theorem here. We have that gamma is inconsistent, and so it must not have a model. And so since gamma doesn't have a model, or since some finite subset of gamma doesn't have a model, but up here we assumed that every finite subset does have a model, we sort of have a contradiction. Yeah, so what is the fourth point? Right, so this goes back to the notion, Ru Tong. So what a proof is a finite set of strings, gamma 1, I have a lot of time, so gamma 2, ... and it ends in gamma n. And so so the idea is that proofs are finite sequences of formulas, exactly. And so what that means is that finite sequences of formulas in gamma. And so we can take subsets of this and say that some subset of those formulas or those sentences proves one sentence, and some subset of those formulas proves the other sentence, because we know that the whole thing proves sentences. So that means that we can sort of split it up into two separate sets, the one that proves phi and the one that doesn't prove phi. And so does that kind of help? Great, okay. Jason, were you able to clarify your point? Oh, yeah, here. Yeah, it's operating in the meta language. It's sort of a tricky question to answer. And I'm going to say, no, we don't need to. I think that would make sense, I guess, if the things that we were proving required the compactness theorem to function and we had some like circularity going on. But in the sense that like we don't need the compactness theorem for like proving that the union of two sets is finite, and we don't need the compactness theorem to have that sets are finite in general. And so there's no like circularity going on here, and I guess that's sort of an answer to your question. I'm not sure. I can't give a great satisfying answer. But to say that you don't need it, you need to have something in mind, right? That way I don't need what? Sorry. I'm trying to.
Sorry, let me just unmute myself.
Sure.
To say, so you said it'd be a problem if we were using a circular argument to prove something, if we needed the compactness theorem for something that we were using to prove it.
Sure, yeah.
But then you said it's not circular.
Yeah.
And so doesn't that imagine that we have some version of set theory or some theory where we know we don't need the compactness theorem that's been defined by a finite set of axioms?
This is a tricky question. Yeah, it does, I guess. It assumes that, yeah, I mean, like, yeah, we can actually use some small amount of piano arithmetic to prove that two finite sets is finite. Like if that's specifically what you're drawing an issue with, then yeah, we can prove that two finite sets are finite, the union of two finite sets, because we can talk about finite sets with piano arithmetic specifically, because piano arithmetic is sort of a nice way to talk about set theory. So yeah.
So in the background of this, are we always assuming basically piano arithmetic unless we indicate otherwise?
God, I can't give you a great answer to that. I'm sorry. I can't give you a great answer, but yeah, I guess you're assuming ZFC. Halen's right. You're assuming ZFC, and there's some circularity. Yeah, Ragurum is also correct. Set theory is an ambient metalogical meta theory. Yeah, we're working in a meta theory. You're all right. Yeah, I guess we're working in a meta theory is right, but I don't know if it's a great answer to this question still. I'll think about it. Sorry, I just want to finish one result, and then we can think about this a bit more, because this is a great question, I think.
Yeah, thanks.
If you stay at the end, we can talk about it. So I just want to prove something simple now, and this is one of my favorite little problems in applications of compactness. And this is the finite four-color theorem implies the infinite four-color theorem. And so what we say is that, and if anyone was at Dr. Parker's talk a while ago, we talked about graphs. And so what we say is that, well, we define a graph first, right? And we say that any graph or any map, any map can be colored by four colors such that no two adjacent countries have the same color. And so there's some technicalities of what it means for something to be a map that satisfies this. Specifically, it's embeddable in the plane, or it's planar, but we don't need to bother with that too much. But to give a visualization of what the finite four-color theorem says, here's a map of the northern tip of South America. And I've sort of drawn some connections between the borders of countries, and I've colored each little dot with one of four colors. And as you'll notice, if you inspect this, no two countries share an edge such that they have the same color. And so this is an application of the four-color theorem. We've taken some finite graph and we've colored it with exactly four colors. Isn't that cool? And here's just the picture without the map behind it. As you can see, it forms a graph. And so the way we prove this is actually with a simple application of zero-order compactness. And the proof is sort of, it's a little ugly looking, but it is really nice. It's cool because it's clean. And so the first thing we do is we define some set of sentence letters. And each of these sentence letters sort of denotes the ith color. So there's four colors. So the ith color from 1 to 4 and the nth country. And what this sort of looks like is for instance, we could say C, red, and then what's a short country name? Iran. Right, so we have C, so we have that the country Iran is colored in red, and that's sort of what this means. And so we let gamma, so this is sort of our set of sentence letters. And then we consider some set gamma that contains a set of sentences, an infinite set of sentences specifically. And the first one, it says, every country has one color. This is what this is. Every country, one color. I shouldn't write all these down. This one says that every country has exactly one color. Number 2, every country has exactly one color, which is something we want. And then finally, we have that no two adjacent countries have the same color. And I've sort of stated this in an informal way, but what this essentially says is that, any country sort of satisfies the four-color theorems, or any finite subset of this obviously satisfies the four-color theorem because all of these sentences dictate the four-color theorem. So we have that every country has one color. We have that any two countries only has one color. And finally, we have that any adjacent country don't have the same color, any two adjacent countries. And so any finite subset of this infinite set of sentences satisfies the four-color theorem. And so if you recall the compactness theorem, since every finite subset has a model, the entire set must have a model, this entire countably infinite set. And so the upshot of this is that for countably many countries or points on a graph, the four-color theorem applies. And so what this says really is that we can four-color infinite graphs. And I think this problem is just kind of cute. And it's pretty much all I have time for today. And so I'll leave you with this is the end of talk slide. And these are just some classes that if you're UTSC, I suggest you take, and some further reading if you're interested in this field. Anyways, thanks for attending my talk. I have lots of time for questions, and hopefully people have questions. And I also have one other final topic if people want to stick around for me to talk about that. So thanks. And I'll open the floor for questions now.
So I want to make a comment about my favorite application of the completeness theorem. So the flip side is if you have a set of inconsistent sentences, even if it is an infinite set, right? Well, then a certain finite subset, some finite subset would also be inconsistent. And so whenever, so suppose I want to show you that you are wrong. If you say, if you have an infinite system and I see that something is wrong with this system, and I want to show you my argument of why you're wrong, I have hope that I can find a finite argument. I just have to show you that, hey, even just this finite subset has already gone wrong. So it's a very happy news when I want to refute something.
Yeah, that's a fantastic, and that's used in a lot of proofs, like where you just find some finite subset and then it proves the whole thing breaks, right? That's like I do like that argument. Yeah. So anything else? Jason, did you get a? Sorry, was it Jason? Yeah, Jason, did you get a satisfying answer to your question? Oh yeah, and I did want to mention a bit about compactness. Is in that this word is used in a lot of places, like compactness of logics, compactness of topological spaces, and then also, if you're interested in that theory, compact like cardinals, and they all are actually interlocked, and you have to get into some tricky stuff with ultra products to talk about it. But I will mention that all of these results are sort of linked through some pretty high level interesting math. Yeah. That's the face I made when I learned about it, Helen. It is crazy, but it's really cool. I can find a talk I think I know of where someone talks about it if anyone's interested. But anyways, maybe
yeah,
I can
think I did get a satisfying answer, although I still have lots of things I'm confused about.
Yeah, I mean, it's a great field to talk about. I would recommend. I don't know if you're a UTSC student, but if you can take this course, it's offered in fall with Ray Grinnell, who I took it with. And I think it's a fantastic course to take. And if not, you can read this book, which is fantastic. And also this book. This is Hodge's Shorter Model Theory, which is sort of the hard version of all of what I've talked about today. And it'll answer all of your questions and leave you with a lot more. Yeah, Matt Sionanda is a fantastic course. It's probably my favorite one I've taken at this university. Yeah. Sorry, awesome. I want to. Oh, go ahead.
Go ahead, Jesse.
So I just wanted to mention, for people that are still around, I'm sure you guys are busy, but the proof that I wanted to do at the very end that I didn't do, and I'll just state it, is the fact that we can prove Ax-Grothendieck, which is a theorem that says every injective polynomial map from two complex spaces is surjective. We can prove this completely model theoretically, which I think is just really fantastic. And I just wanted to state it. It's sort of a theorem in algebraic geometry, as the name Grothendieck suggests. But anyways, this is just what I wanted to prove at the very end. And it sort of suggests a connection between model theory and algebra and algebraic geometry and sort of all these other fields. And I think it's really, really quite interesting stuff. Yeah. Sorry, go ahead, Parker.
The ask that I had before people run off, we've got 34 people. That's a huge turnout. One of the former speakers, Ben Chislett, asked if we could get feedback on talks. And I think this is a great thing. So if you've got even just 1 minute, please fill out this Google form. If you're not comfortable using Google, please send us an email. But this is a growing seminar series. We'd love to hear your feedback on how this talk went and what you'd like to see in talks. And we'll anonymize it before sending it over to Jesse. The other announcement, sort of another bureaucratic thing, we don't have a seminar speaker next week because we ran out of seminar speakers. So if you've got a great talk, and I'm looking at you, Albert. I know you have a good talk. And Jason, you're not even on your camera, and I know you've got a good talk. Please volunteer. Please tell your friends that this seminar is running. We're looking for speakers. So We don't have a speaker next week. We do have a speaker on the 30th. So on the 30th, we're going to have a speaker telling us about group theory and puzzles. I'm sure it's going to be very good. Very nice hands-on kind of talk. So please take a moment, fill out the feedback form, and let's take a moment and thank our speaker. That was awesome. Yay, thank you. Yay. Yeah, absolutely wonderful. I'm going to stop the recording here, but we'll stick around if there are more questions.
I do